Hi class, welcome to the next chapter, chapter 6. Chapter 6, we talk about maximum and minimums. Specifically here in 6.1, we're going to talk about maximum and minimum values. We've brought up the idea of maximum and minimums before, but we haven't talked about them in depth yet. So we're really going to analyze how to find max and mins. These are really important topics. It's probably one of the more important topics that come out of Calculus 1. If you know how to optimize a function, meaning find the max values and minimum values, again, there's whole careers that are based on that. There are whole fields of math that are based on optimization. So it's really important to understand how we can use the derivative and how understanding that us analyzing the rate of change of a function allows us to really analyze a function, right? So we know how to look at like long-term behaviors and look at limits at certain points. So what is our function doing, behaving at this point? And then we can use the derivatives to talk about the rate of change of our function. And now we're going to really use the derivative to talk about and analyze our functions, okay? So we're going to review, but at the same time talk about new stuff, okay? So we've said this stuff before, but we're going to say it in a different way, I guess is the best way of describing how we're going to go through this section. So if our derivative function is positive for every value inside of a closed interval, then our function is going to be increasing on that closed interval. So we've seen this before, right? When we start talking about the function, the derivative as a function, we say whenever the derivative is positive, that means that I have a positive rate of change, right? The tangent line has a positive slope. That means that my function is increasing. So that's just us mathematically now rigorously stating that fact, okay? If you've never seen this upside down A before, if you're new to my class, this is one of the first video series that you've seen of mine. This upside down means for every, okay, for every x that is inside of this interval, my function is increasing on that interval, okay? So if my derivative is positive, basically the interval for which my derivative is positive on means that my function is increasing on that interval, okay? For the interval, every interval that my derivative function is negative on means that my function is decreasing. Okay, so we read this that if the derivative of my function is negative for every x in some closed interval from a to b, then my function is also decreasing on that same interval from a to b. Okay. We know that when the derivative is 0, when the slope of the tangent line is 0, that means that I'm at the top of a hill or at the bottom of a hill, meaning that I am at a local max or a local min. There are also other times when the derivative is 0. So we don't say that it is definitely a max or min. We say it's a possible maximum or minimum location. So we're always interested in when the derivative is equal to 0, right? If my derivative is equal to 0 at a point C, right, x equals C, or if the derivative at that same point C is undefined, then we call that a critical value. Okay, so it's a value that's of interest to me and I would want to explore my function further at that point. So the critical values are one of the main things that we're looking for. So basically any value that makes my function, my derivative function 0 or undefined is values that I'm looking at. Okay, so this would be more so like vertical asymptotes in the derivative function, not values that are outside of the domain. So for instance, if my derivative function is a square root, I'm not going to look at all the values that make that square root negative as critical values. That's not what I'm looking for. I'm looking for values that make it undefined, so more so vertical asymptotes and zeros. Okay. So this brings us to the first derivative test. Us using the knowledge of when my function is increasing and when my function is decreasing based on the derivative, I can use that fact to try to find maximum and minimum values. Okay, so let's say that we have a critical value, C, for a function that's continuous. Then if my derivative changes from positive to negative value at that critical value, then I'm going to have a local maximum. So let's think about that. What does that mean? If I have a max value, that means I'm at the top of a hill somewhere. Okay, I have positive values on the left of x equals c, and then I'll have negative values on the right, because I'm going from a positive rate of change to a negative rate of change, right? I've gone up the hill, reached the top, that's why it's at c is 0, and then I start to go negative, right? So that's what it means to have a local maximum. To the left of c, I'm negative, and on the right of c, I will then be positive. So I'm changing from positive to negative on either side of x. If I go and I change in the opposite direction, right, it means that I'm at a local minimum. So again, if I'm at the bottom of a hill, for values of x that are less than c, I have a negative slope, so my derivative will have negative values. At c, I will then have output of 0 for my derivative function, and then my derivative functions will go positive because I came down, so I'm decreasing the value, I hit the lowest point, tangent line has a slope of 0, and then I increase in value, right? So if I have a if my derivative goes from negative to positive on either side of c, right, so negative on the left and then positive on the right, at that critical point, I have a local minimum value, right? If I stay positive on the left and on the right of c, then, or negative on the left and right in c, then I am inconclusive, okay? I do not have a local max or min at that point. So I have to change signs. So depending on how I change signs determines whether or not I have a local max or min. If I don't change signs from the left to the right, I stay negative on one and negative on the other, or positive on one and positive on the other, again, when I'm looking at the derivative, then there is no local max or min at that critical value, right? So that is our first derivative test. We also have what are called global maximum values, or absolute maximum values, and global minimums and absolute minimums. So this happens when I'm on a closed interval, okay? Meaning that my function doesn't exist everywhere. It has a smallest input and a largest input. That means somewhere along the way, there is a smallest value and a largest value. And there can also be local maximum and minimum values as well. Okay, so let's go ahead and just real quick take a look at this on Desmos. I'm sure I have a graph here as well, but as I'm talking, let's go ahead and just take a quick example. Okay, so let's take this function. For example, I have maximum and minimum values here. So if we just look at what the derivative is doing for a maximum value, my rate of change is positive, right? So my derivative will have a positive value and then 0 at the max, and then it'll change to negative. So let me go ahead and give this a function name, and then I will have the derivative, right? So my derivative is positive and then 0 at the max value, okay? And then I am negative after that. When I go from my derivative function being negative to then being positive, so I have the zeros in common here. Okay, I have the common zeros. So I'm decreasing in value, so my derivative function is negative. And then on the other side of that critical value, it then turns positive. And you can see that my slope starts to go positive, right? So that's looking at the left and right side. Okay. Obviously, at the max value, the local max, the derivative is 0. And at the local min, the derivative is 0 as well. And then we also have, let's say that I restrict this now. Let's say here. Okay. Let's go here. Okay. So now, actually, let's go 2.5. Okay. So now I have maximum global and maximum minimums, right? So this is not a local minimum, okay? This is a local max. This is the global max. Okay. This is the global min because it's the smallest value that my function obtains anywhere. This is the largest value my function obtains anywhere. Here, my output values are larger than all of the other values around it, but it is not a global maximum. It's just locally larger than everything else. This does not count as a local minimum. Okay, so that's the difference between global and local mins and maxes, which I do have in our slides, which we'll see again in just a second. So again, the global max or absolute max is the same, different name for the same thing. It's the largest value. It's the largest value that your function obtained over the domain given. Okay. Same with the global and absolute min. They're the same thing, just different names. It's the smallest value that your function takes on over its domain, the most negative value. Okay, so now let's talk about a definition. So let C be in the domain of a function f. Then your function evaluated at C is going to be the global maximum of your function over this domain if your function evaluated at C is larger than or equal to all the other output values of your function. Okay, so this is for every x in your domain. So the global maximum is the largest output that you have. It can be equal to other outputs, but there should be no other outputs larger than it for every single input inside of your domain. Okay, the global minimum for your function over your domain is the same thing, except that it's the smallest value. There should be no other values smaller than it. There can be values that are equal to it, but there should not be any values that are smaller than that output. Again, for your global max and mins, or your regular max and mins even, you're looking for output values, not the inputs. The inputs are important because they tell you where they happen, but you're looking at the actual values of your function. What is the largest value your function has, or what is the smallest value your function takes? We call these extreme values, right? The global max and the global min are your extreme values. Right? So this brings us to the extreme value theorem. If f is continuous on a closed interval, a to b, then f attains a global maximum value f of c and a global minimum value f of d at some point c and d inside of our closed interval. So as long as I'm defined on a closed interval, I'll have a global maximum and a global minimum. That's what the extreme value theorem is. If I'm not on a closed interval, then it's possible that I don't have a maximum value, right? So like, let's say that my function goes on forever, let's say e to the x. There's never a largest value because there's always something larger because my function goes on forever and ever. So the extreme value theorem only exists for closed intervals. If I'm on a closed interval, right, there's an endpoint, a start and an end, I have a smallest and I have a largest value, right? So again, looking at our graph, we have a global max, a global min. This would be a local maximum. This would not necessarily be, I guess you could consider this as a local min because it's smaller than all of the other values around it. But typically we reserve that for global maximum and minimum values. Okay. So now let's talk about the closed interval method. Okay, so for the closed interval method, we actually did an example of this already. Maybe it left you confused when we went over it. It's fine if it did, but we did do an example when we went over the economics portion in the application of derivatives to the sciences portion of chapter 5. So you've seen this in use somewhere already, but now we're going to formally address it and talk about it, right? So the closed interval method is a method for finding your absolute maximum and minimums. Okay, so the first derivative method that we went over here, this is the first derivative test. It's very useful for finding local maxes and local mins, but not so much for global maxes and global mins because a global maximum or minimum, as you see here, may not have a derivative of 0, right? So I can't find a global max like this one if its derivative is not 0, right? So the first derivative test just allows us to find local max and mins because I'm looking for the change of sign from one side of my critical value to the other, right? So I'm looking for when my derivative is 0 and then what's happening on one side compared to the other, right? Sign-wise for my derivative. So the closed interval method allows me to find global maximums and global minimums. So what I want to do here is I'm going to find the value of all of the critical numbers, right? So I'm going to find the derivative of f, and I'm going to find all the critical numbers inside of this open interval, so not including the endpoints. I'm just going to look over my domain, and I'm going to say when is my derivative 0 inside of the domain that they give me. Okay. Then what I'm going to do is I'm going to take those values and I'm going to find their outputs, right? So first I take the derivative, I set it equal to 0, I find all the points where the derivative is 0 inside of this interval, and then I plug those values into my original function so I can see what all their outputs are. I then do the same thing, well, not the same thing, I don't take the derivative, but I take the endpoints a and b, and I find their values as well. And so basically the largest value of the function evaluated at the critical points and my function evaluated at the endpoints a and b is my max. The smallest of all of those values is going to be the absolute minimum, right? So let's go ahead and do an example. So let's take the function t minus cubed root of t on the interval -3 to 4. Okay, so I have a closed interval. So I first find all the critical values. So I'm going to take the derivative of my function f, right? So 1 minus 1/3 t negative 2/3. And I am going to set this equal to 0. Okay. And just solve for t, right? So I'll have 1 on one side. So -1 equals -1/3. I can just change the sign on both of those. Multiply both sides by 3. And then take the -3/2 root, okay, in order to solve for t, right? So take the -3/2 roots to isolate t, so t is 3 to -3/2 root. I have no idea what this is as a value, so I can plug it into my calculator or I just use it as it is. And then I take the endpoints of my interval, right? So -1 and 4. So these are the 3 points I have to check. I only have 1 point from the derivative, right, where the derivative is 0, and then I check my 2 endpoints, so that gives me 3 points. So I'm going to plug all of these into my original function. So I'm going to plug in -1 first, right, the smallest point in my interval, and I get out -2. I'm going to plug in the next point, 3 to the -3/2. I'm going to get out this crazy value, -0.38490000795, which is larger than -2. And then I'll plug in 4, and I'll get 2.412598948. So the largest of all of those is obviously f of 4. And the smallest of all of those is f of -1. So I have a minimum value, absolute minimum, at -1, and an absolute maximum at f of 4. Okay, so that's where they are. The actual absolute max value is this value, this 2.412598948. Okay, that's my global max, and my global minimum is -2. Right, so the largest value my function has and the smallest value my function has. Right, let's do one more example. Okay, so a company has 100 units to spend for equipment and labor combined. The company spends X on equipment and 100 minus X on labor. So they have 100 units total. They split it not evenly, but they split it between equipment and labor, right? So if they spend X on equipment, then what they have left is 100 minus X. So for instance, if you spend $40, then you have $60 left, right? 100 minus 40. So they spend some on equipment and the rest they spend on labor. So this allows it to produce Q items, right? So that's not the name of it, but that's the amount. The Q is the amount of items that they can produce. where the number of items they can produce is is modeled by this equation, right? So depending on how much they spend on equipment, right, allows them to spend this much on labor, and the product of these two amounts is dictates how much they can create, right? How many items they can create. So how much should the company spend on equipment to maximize production Q? So I know it's a little bit more involved because it's a word problem, but I think you should go ahead and pause this video and find the absolute maximum, right? So here they want to know how much should the company spend to maximize production. So find the value of X here that makes Q as large as possible, right? So maximize this function means to go ahead and use the closed interval method on this function. So go ahead and work on this and then come back and unpause this video and see if you get the same thing as us. Okay, so hopefully you went ahead and you worked on this at least a little bit, at least attempted it. If not, that's okay. So let's go ahead and see how we do this with each other. Okay, so we want to know how much we should spend to maximize our production on labor, and what is the maximum production Q. I know I didn't pose this question to you already, but as you work through this problem, you should be able to find these things anyways, right? This is what you're looking for. So this is my function Q, right? So first of all, I know that my domain is from 0 to 100. I can't spend more than 100 units because I don't have more than 100 units. And so when I'm saying units, that doesn't mean $100. Maybe one unit is represented by, I don't know, is represented by $100,000, right? So then 100 units is really like $10 million, okay? So I have 100 units of money to spend, okay? Whatever that unit represents, I don't know. So I can't spend more than 100, and I can't spend less than 0, right? So my effective domain, right, my practical domain is from 0 to 100. So those would be the endpoints that I'm looking at. I also know that I need to find the derivative of this function, okay? So here I can simplify a little bit. Maybe I don't like decimals and I want to turn it into fractions. You know, that's how I work personally, so that's what I went ahead and did here. However, you can still work with your decimals. When I take my derivative, I am applying the product rule, right? So I'm using my fractions because 5 and 10 will cancel, so it makes things a little bit easier to look at here. So I'm applying my product rule and my chain rule together, and this is the derivative that you should come out with. Okay, so hopefully you at least did the derivative and you have the same value here. Maybe it's a little bit different because you kept the decimal values. So for instance, instead of 3/2, it should reduce to 1.5, right? This should still be a 5. This should still be 0.8, which actually reduces down to just a 4, which is nice, which is again why I like to use fractions. Apply this negative here. Start to simplify. You can see we have very similar factors. This 100 minus x is in both terms, and I have x to some power in both terms. And remember, I always pull out the negatives. So from both sides, I'll factor out this negative 7/10, which will bump this up to 10 over 10. And I'm going to pull out this from both sides, or from both terms, this negative, which will bump this up to 5/5, right? Because it's already got a common denominator. So that makes it really nice to look at. And then I can just simplify this inside. This is 300 minus 3x minus 8x. So this will be 300 minus 11x. So now my function is nice and small and compact and really, really easy to work with. So now I'm looking at all the values that make my function either 0 or undefined within 0 to 100. So my endpoints are points I have to look at. I got to look at what happens to Q at 0. I got to look at what happens to Q at 100. And then I have to look at Q for the points that make all of these 0. So 1 would be 0, which is already in my practical domain. 100, which is already my practical domain as well, because those are the two endpoints. And then here, I'll be using 300 divided by 11. That's my other value of interest, which I know is less than 100, and it's positive, so that's nice also. Okay, so these are the three values that I need to check. So if I spend, well, let's just think about it. If I plug in 0, my output function is 0, right? 0 times everything is 0. If I plug in 100, I also get out 0. So it kind of really only leaves me with one value, which is 300 over 11. So if I plug 300 over 11 into my actual function, okay, then the amount that I'll spend on labor, right, is going to be this 100 minus 300 over 11. Okay. So again, Q of 0 is the same as Q of 100, which is 0. And we might be saying, well, Professor Williams, how many units is 300 over 11? You can just plug that into your calculator. So again, this says how much should the company spend on equipment to maximize production. This is the amount that we need to spend on equipment. It's not asking me for the maximum. Oh, it is. What is the maximum production Q? So that's one of the things we're going to do is we'll plug this into our function to get our actual output, right? So 0 and 100 will not give me the max value at all, just give me out 0. When I plug in my critical value, my only critical value, I get 415.9 units of equipment, right? So here, this is around 27.27272727 units of money that I'll be spending on equipment, and 72.7272727272 is the amount that I spend on labor. And when I spend this much on equipment and the remaining on labor, I'm able to produce the maximum amount of units, okay, of items, sorry, which is 415.9 items. You could round this up to 416, although technically speaking, if this is my maximum, I'm not actually able to make 416. I'm just shy of enough material or what have you to make 416. So actually, technically speaking, the max number, if my items can only come in whole units, the max would be 415 here. You would not round this up to 419. So for instance, let's say I was doing the same problem, but this function represented number of people that could fit inside of a building. I'm not going to chop off somebody's hand so that I can get exactly 415.9 people in there. If someone's hand doesn't fit in there, they're not fitting in there. They have to leave, right? If you ever see like those like compacted bullet trains in Japan, right? If you can't ride a train with your hand sticking out, it's going to get cut off. So that person would have to go. Obviously, they actually have people who force everyone in there. But long story short, you would round down depending on what the application actually is. What are these items? Lots of times you can't sell a portion of an item, so this would be round down to 415.